I hate this channel.
No! No!
Our initial idea was to use an injection molding machine to produce bobbleheads of Dr. Davis. However, after seeing how much space we had to work with, a bobblehead was far too large.
Ooh, that's kind of small. Yikes.
After some thought, we decided to instead make some Sphericons. To begin this process, we needed to design a mold that would fit within the size constraints of the APSX PIM injection machine. We used Inventor to design our mold halves, incorporating 2 gates which would allow us to create 2 Sphericons at the same time. Safety first.
Wow, that's pretty impressive.
Sphericons produced a natural draft angle that would make them easy to remove. We wanted to do the same for the channels, so we designed a 3-degree draft angle into it. We made sure that the gates were narrow in order to allow for high injection speeds. Once the design was done, we converted it to an STL file and started printing it on a Dremel. This was done to form a prototype to see if any design aspects needed to be changed before moving on to the more expensive resin printers. The material used and the print quality were not important to us, as these would not be used to make the Sphericons. After 6 hours of printing on Dremels, we had our mold halves done.
Let's get to it. Safety first.
Six hours later.
We immediately noticed some issues with our design. First, the size of the Sphericons were too small and didn't optimize the available space. This was due to a calculation error when designing specific dimensions of the Sphericon. To fix this issue, we determined that we wanted a depth of 0.438 inches and multiplied it by the square root of 2 to get the correct length. The other issue we had was that when the 2 mold halves were put together, they did not fit right because we did not mirror the design across the 2 mold halves. With this added information from prototyping, we redesigned the molds on Inventor, only giving 1/16 of an inch from the Sphericon to the bottom of the mold. Once we got all the changes done, we contacted lab support to get us access to the resin printers. To use these machines, we needed to download a program called Preform. Doing the tutorial, we learned that printing at an angle actually helps improve the print quality because it reduces the cross-sectional area of each layer. Using Preform, we rotated the part 45 degrees and auto-generated supports for the part. We used high-temp resin because it was the only kind that could withstand the temperatures the injection molder got up to. By using a resin printer, we were able to get much higher quality print than we would with any other regular extrusion printer. The overall print took about 10 hours to complete. Once it was done, we got lab support to help us remove the print from the bed. It's important to wear gloves and have a well-ventilated area when handling resin, as it is a toxic material. Once removed, we easily removed the supports using pliers. The next step was to do some post-processing for the print. First, the resin needed to be cleaned. To do this, we let it sit in a pool of alcohol for 6 minutes. This helps to remove any excess resin that was not cured during the printing process. We let it sit for a few minutes to dry before moving to the curing station. This station uses ultraviolet light to finish curing the resin to a point where it can be safely held without gloves. It also further hardens the resin, improving its overall strength. We left it to cure for 2 hours. Once done, we looked at our prints and for the most part they came out great. The one issue we thought would cause problems was that the mold halves were a bit warped. We were worried that the clamping force of the machine would fracture the mold. We were finally ready to make some Sphericons. We did a bit of research about injection molding with printed molds to find out what settings would be best for the process. Then we went to the machine shop and began setting up the machine. First, we wanted to make sure our mold fit into the machine. We found out that one half fit perfectly, but we couldn't get the other half to fit. The printing process had made the length of one half of the mold a bit longer than it should have been. To get the mold to fit, we sanded down the piece to decrease the length by about 0.01 inches. After sanding, the half fit perfectly into the machine. After setting up the machine with the recommended initial settings, we conducted our first injection molding trial. The part came out with significant flash. This wasn't totally unexpected because of the warping of the mold in the middle, and so to fix this, we turned to the troubleshooting guideline found in the APSX PIM manual. The issue was with the clamping force not being strong enough to keep the mold together. Even though we were worried increasing clamping force would fracture our mold, we went ahead and went with it. In later trials, we found out that a clamping force around 5 was enough to prevent the creation of flash. When we started out, we had it set to 3. The other primary issue we encountered in the injection molding process was deformation of the pieces coming out of the mold. What we found is that pieces coming out of the near side of the mold tended to come out very nice, whereas on the other side, they tended to be significantly deformed. We tried a number of things to stop this, such as increasing the barrel temperature, increasing the injection pressure, and increasing the hold time. None of these had a consistent effect on the quality of the final product. After around 22 to 23 trials, we came to the conclusion that the cycle time between trials had a significant effect on it. At this point, we started to measure the cycle time and noticed a clear increase in quality with increase in time. We're not sure the reason for this, but we think it may be due to some sort of asymmetrical heating and expansion in the mold, causing small deformations in the gate. More research will be needed to fully determine the cause of this. Another defect we found was multiple shades of black appearing in swirls on the outside shell of the Sphericon. Both sides of the mold experienced this swirling, so it wasn't an issue with just one side. Throughout the entirety of our testing, these swirls appeared, so none of the variables we were changing had an effect on this defect. We believe that these defects might be caused by some thermodynamic or fluid dynamic effect. One possible solution would be to move the gate to the top of the part. Overall, we were happy with how the products turned out in the end, but we learned a lot and there are many things we could have done differently if we were going to try this again. The primary thing we would change if we were to do this again would be to change the mold design. In a new mold design, we would change the gates to allow for injection of the plastic at the top of the object. This may help or solve many of the issues we faced. We would also like to experiment with larger gates in the molds. Finally, we're curious if we can make the mold blanks with a similar cross-sectional area but with a larger depth. One main constraint with this project was the size of the mold slots. Increasing depth would allow for much larger parts to be made with the mold and would increase the usefulness of this relatively cheap injection molding machine.
Gary! I was just looking for the sports channel, Gary.